Discover Geography, Lesson 7-3, Climate Change. We've talked in our earlier lessons about some of the natural factors that determine the distribution of climates around our world. But climate can also change over time. A few years back, there were a few days of unusually cold weather in Nashville, Tennessee during the middle of the summer. This weather got a lot of national media attention because Nashville happens to be the home of Al Gore, who is famous as a climate change activist. You saw a lot of people in the media pointing to these low temperatures in Nashville and saying, aha, Al Gore is full of it. Look at how cold it is right in his own hometown. A little later on that summer, there were record-breaking high temperatures in Seattle, Washington. In this case, this also got a lot of media attention, and you saw a lot of people saying, look at how hot it is in Seattle. We have unprecedented heat waves there. Obviously, climate change is something that's real and is really happening. Both of these sets of people, both the people that pointed to the cold temperatures in Nashville as evidence that climate change is not happening, and the people that pointed to the warm temperatures in Seattle as evidence that climate change was happening, were wrong. A single data point like this, a day or two of certain temperatures in one place, cannot tell us anything about the climate. Climate is our long-term average atmospheric conditions. What can tell us something about whether the climate is changing is this graph here. Each point on that graph, every time you see the direction of that line change a bit, each of those points is a global average temperature for an entire year. So it's combining 365 days worth of observations at any one spot, whether it be Nashville or Seattle or somewhere else, times hundreds of weather stations all around the globe, averaging them together into a single point. Then we put all those points on the graph and we look at the overall trend across several decades in where that temperature is going. So the temperatures on any one day or any 1 week in one place don't tell us anything by themselves about what's happening to our global climate. It's only by looking at all of the data from all of the places in the world over a long period of time that we can actually document changes in our Earth's climate. Now, the Earth's climate has changed a great deal over the course of geological history. So what you see on the slide here is basically climate change since multicellular life first evolved. The present day is on the left-hand side of this graph, and we see that our present day climates are actually, in the grand scheme of things, on the colder end. If you compare the current temperatures on this graph to the temperatures during the era of the dinosaurs, which is the Cretaceous, Jurassic, and Triassic periods labeled K, J, and TR along the bottom of the graph. We know that during that period of the Earth's history, there weren't ice caps at the North and South poles, whereas of course there are today. If we zoom in on the climate in a much more recent period, here we see temperatures reconstructed going back almost 2,000 years. And in this case, the graph goes from left to right. So the present day is on the right-hand side of this graph. What we see is that our current climate is substantially warmer than it's been at any point in human history. If we take this reconstruction back farther even than the year 2000 of the Common Era, or the year 200 of the Common Era, we'd see that we continue to have temperatures below what we have globally at present. Not only are our current temperatures much higher than they've been in human history, they're also changing more rapidly than they have throughout human history. If you look at the ups and downs of the overall global temperature on this graph, you see a gradual rise to the medieval warm period around the year 1000, then a gradual drop to what we call the Little Ice Age around 1800, and then a sudden and very dramatic uptick in that graph. So what we're seeing now is not only temperatures that are unusually warm as compared to the scope of human history, even if not warm for the scope of geological history, but we also see temperatures that are changing much more rapidly than our Earth usually sees. And rapid change is much harder to deal with. It's a much bigger concern than gradual change. So that's why we're concerned about the recent increases in our global climate. That we're concerned about not only higher temperatures we've seen before, but also more rapid change than we've seen before. Now, changes in the Earth's temperature are being driven in this case by changes in what we call the greenhouse effect. The greenhouse effect is a phenomenon that traps solar energy on the Earth. In our Earth's atmosphere, we have several different what we call greenhouse gases. Greenhouse gases are gases that have a property of being transparent to light, but not transparent to heat. That is, solar energy can pass right through those greenhouse gases in the form of light coming from the sun. So greenhouse gases let that light come right in to the Earth. That light energy is then absorbed by the surface of the Earth and then re-radiated back out in the form of heat. That heat is then trapped by those greenhouse gases. They do not allow the heat to go back through in the same way that they allowed the light to come in. This blanket of greenhouse gases maintains the Earth's temperature at a higher level than it would be without them. The Earth would be uninhabitably cold if it weren't for the naturally occurring greenhouse gases in our Earth's atmosphere. We can change the Earth's climate if we increase or decrease the amount of greenhouse gases in the atmosphere, if we trap more or less of that solar energy. And what we're seeing right now on the Earth is an increase in the amount of greenhouse gases in our atmosphere, and therefore an increase in the amount of heat energy that's being trapped after it enters our Earth, and therefore an increase in our global temperatures. That increase in the greenhouse gases is largely a result of how human activities have modified the carbon cycle. Here you see the diagram of the carbon cycle that we looked at in an earlier lesson. And we said that the core of the carbon cycle is this movement of carbon from the atmosphere to plants to animals back to the atmosphere. That's a stable cycle. That carbon gets taken out and put back in roughly the same amount. However, some of that carbon in the past was removed from the carbon cycle by being buried deep underground. At present, humans are digging that old carbon back up, releasing the energy that's stored along with it to power our factories and our cars, etc., and then putting the carbon back into the atmosphere in the form of gases like carbon dioxide and methane. These gases not only contain carbon, but are also important greenhouse gases. So by adding that carbon back into the atmosphere, we're also enhancing our world's greenhouse effect. Here you can see a flow chart of where these greenhouse gases come from, what processes create them, and then what are the actual gases being put into the atmosphere. So you can see the source of these greenhouse gases is predominantly our use of fossil fuels, coal, oil, and natural gas. When we look at the human activities that are producing these greenhouse gases, we see industry, transportation, energy supply, and land use change as our major categories. So our industrial processes that consume fossil fuels are putting a lot of greenhouse gases into the atmosphere. Our use of fossil fuels for transportation, gas in your car, etc., putting a lot of greenhouse gases into the atmosphere. Our attempts to generate energy, largely from fossil fuels, are putting out greenhouse gases. Then land use change is not consuming fossil fuels so much, but is creating more greenhouse gases. If, for example, we clear a forest, we burn all of the plant material, all of the carbon that was in those plants goes into the atmosphere, and if we keep that land cleared, if we've changed the land use, changed it from a forest to a field or to a parking lot or something like that, then no new plants are going to grow and take that carbon back out of the atmosphere. And so we've permanently increased the amount of carbon in the atmosphere by changing that land use. If we then look at the right-hand side of the diagram, we see which gases we're actually adding to the atmosphere. You can see the largest greenhouse gas that people are generating, the largest what we call anthropogenic greenhouse gas, is carbon dioxide. That's the largest thing that we are contributing to our Earth's greenhouse effect. Second to that is methane. which is the chemical formula CH4. And then the third is nitrous oxide, N2O. Those are the three biggest greenhouse gases that human activity is adding to our Earth's atmosphere, though there are a variety of other ones that also play some role in warming the Earth. Each of these greenhouse gases is going to create some degree of what we call climate forcing. Forcing refers to the amount of change in the Earth's temperature that a given factor is going to create. We can calculate, based on basic knowledge of physics and chemistry, how much forcing we would expect a given amount of increase in carbon dioxide or methane or any other gas to create when added to the atmosphere. And we can make similar calculations for other factors that might be influencing our Earth's climate. So what you see on the right-hand side of this slide is the calculated amount of climate forcing that's going on for various factors that are influencing our climate. So these include things like the addition of greenhouse gases to the atmosphere, changes in land use that change the amount of solar energy reflected back into space while it's still in the form of light, changes in aerosols and clouds that reflect away solar energy, and also natural changes such as cycles in the brightness of the sun. We can take all those different climate forcings and add them together to calculate what we would expect to be the amount of change caused in our Earth's climate as a result of the factors that we know about. And what you see at the bottom of that graph is the total net anthropogenic, that is, human-caused climate forcing, is far greater than what we calculate to be any natural climate forcing that may be going on. And that makes sense when we look at the amount of these greenhouse gases that we've been putting into the atmosphere. On the left-hand side of the slide, you see the historical changes in the amounts of these greenhouse gases in the atmosphere. And what you see for carbon dioxide, methane, and nitrous oxide, our three major anthropogenic greenhouse gases, is that the levels of these gases in the atmosphere were fairly stable for most of human history. But only in the last couple hundred years, with the beginning of industrialization, therefore the beginning of large-scale modification of the Earth's surface, and especially large-scale extraction and consumption of fossil fuels, we see a dramatic uptick in the amount of these greenhouse gases in the atmosphere. Now, one caution that I will give you in reading these graphs, and this is a good thing to keep in mind when you're looking at any graph, is that if you look at the scale on the left-hand side of these graphs, you see that the bottom of the graph is not 0. The bottom of the graph, for example, of the carbon dioxide graph is a little under 250 parts per million of CO2. So when you look at the amount of increase in carbon dioxide, it's a dramatic increase in carbon dioxide, but it's not a quadrupling that it kind of looks like on that graph. So always be careful when you look at a graph like this to account for whether that graph might be cut off above the 0. You don't want to get misled by that on any graph that you look at. Now we can measure changes in the Earth's climate to see how much they match up to what we expect based on calculating these climate forcings. So here are 3 things that we can already see clear evidence of change in on our Earth. So at the top you see global average surface temperature. This is basically the same data that we saw in that graph earlier on in this lesson, and we can see a clear upward trend in global average surface temperature. The next thing you see there is global average sea level. We'll talk a little bit later about why we expect increases in the Earth's temperature to result in increases in sea level. But you can clearly see an upward trend in global average sea level. And in the last graph, you see northern hemisphere snow cover, the amount of snow on the ground during the winter. And you can see a downward trend in that particular variable. So there's clear evidence that our Earth's climate really is changing right now. We can combine these things into climate models. We can use our knowledge of climate forcings to construct a model that will tell us, for a given amount of climate forcings, what should we expect to happen with the Earth's climate? And then we can take these models and test them by starting them off with data from the past and then using the model to try to predict what will happen out until the present. Then we can compare those predictions with what has actually happened to assess the accuracy of our model. And so that's what we see on this slide, is a series of runs of climate models. The blue band on each of these graphs represents a climate model that incorporates only natural climate forcings, only natural phenomena that might influence the climate. And that's shown as a wide band because there's a certain level of randomness in these climate models. And so what we do is, rather than just running the model once, we run the model 1,000 times. And so that band represents the range in which the results of these thousands of runs of this model fell. So the blue band represents these models with only natural forcings. The pink band represents the models that incorporated both natural and anthropogenic forcings. So that is, they incorporate both natural events and human events that we expect to alter the climate. The black line represents our actual measured temperatures. That's what really happened. So when we compare these different models, what we see is that the natural only and the natural plus anthropogenic models start out fairly similar, but they diverge as they go on. In all of these models, whether it be a global model, one for just the land, one for just the ocean, or one for each of the 6 regions that they break out on that map, over time, the natural forcings kind of rise a bit in the middle of the century and then fall a bit towards the end, whereas the models using both natural and anthropogenic forcings show an overall upward trend out towards the end of the century. When we match that up with our actual observed temperatures, what we find is that black line stays right within the model runs of the natural plus anthropogenic forcings in every case, and diverges from the models using only natural forcings by the end of the century. So this is a pretty good evidence that our climate models have things basically right, that we've got the right idea, and the anthropogenic forcings are the primary cause of the increases in global temperatures that we are seeing right now. Once we've validated those models by trying to predict the present from the past, we can then try to predict the future based on the present to see what's going to happen to our global climate. Now, the one catch with predicting the future based on anthropogenic forcings is we can't necessarily predict what those anthropogenic forcings are going to be in the future. On the one hand, our global societies may decide to make drastic cuts in our amount of greenhouse gas emissions. On the other hand, we may decide to do nothing and continue to emit high levels of greenhouse gases. That's a policy choice that we might make. It's not something that we can scientifically predict. And so when we project our climate into the future, we're going to project it based on various different scenarios. We'll make one scenario where the world does nothing to reduce our greenhouse gas emissions and see what would happen under that policy. We'll do another one where we decide to drastically limit our emissions, see what happens there, and any other plausible scenarios that we might want to look into. Our model can then predict what's going to happen to our global temperatures based on those different scenarios, and then that gives us some information about the relative merits of those different policies. How much good is it going to do to pursue one policy versus another? How much is it going to hurt us? And what you see here is that the scenarios that involve continued high levels of carbon emissions, so that's things like the A2 and the A1B scenario in this particular set of model runs, we expect to lead to something between 3 and 4 degrees worth of surface warming over the next century. That may not sound like it very much, but that's equivalent to the amount of warming that took us from the last glacial maximum to our present situation. So enough warming to cause those glaciers to retreat from Pennsylvania all the way back to Greenland is the same amount of warming we expect to happen over just 1 century if we continue to emit greenhouse gases at our current level. You might also take a look at the line for year 2000 constant concentrations. That's essentially if we stop emitting anthropogenic greenhouse gases entirely. If we stop our emissions so that our atmosphere just continues to have the same amount of greenhouse gases in it that it did in the year 2000, which is substantially lower than what it is right now in the year 2014. What we see there is even if we were to stop emitting greenhouse gases entirely, we'd still see a continued small warming of our climate. So if we were to want to bring the climate back down to where it was before this dramatic warming, we would actually have to remove greenhouse gases from the atmosphere. But in any case, even that year 2000 constant concentrations scenario, where we stop all of our anthropogenic greenhouse gas emissions, keeps us well below that drastic surface warming that we see in the kind of business as usual continued high emissions scenario. These climate models also allow us to look at the differences in climate change in different locations on the Earth. So rather than just focusing on total global climate change, we can look at how climate is expected to change in specific places. And so what you see here is a variety of model runs under different scenarios for different time periods. So the first set of maps is projecting 1 or 2 decades into the future. The other one's projecting almost a century into the future. And what we see on all of these is that in any scenario, in any time frame, we expect to see the greatest amount of warming in the polar areas. It's going to be the areas near the North Pole and the South Pole that we expect to warm the most. The areas near the equator will still warm, but not by quite as much. So the effects of climate change, the physical effects, are going to be different in different parts of the world. We can also try to project differences in precipitation, because as our climate warms, that's going to change the amount of energy in our Earth's climate system, and so it's going to alter the functioning of our primary circulation. It's going to change the intensity and location and movement of our high and low pressure zones, and therefore of our precipitation levels. And what we see on this map is that, as kind of a general summary, what we expect to see is that the areas of the world that are already fairly dry, and so you can see that kind of along 30 degrees north and 30 degrees south on this map. The areas that are already dry, we expect to get drier. So the southwest United States, we expect to see more droughts there. Areas in the Middle East, we expect to see more droughts. Australia, Southern Africa, we expect to see more droughts. On the other hand, many areas that are already fairly wet, we expect to see increased precipitation. So in Asia, in the central part of Africa, for example, we expect to see increases in precipitation. In the northern parts of the world, closer to 60 degrees north, we expect to see increased precipitation. So climate change is changing not just our temperature levels, but it's also changing our precipitation. It's changing both aspects of our climate. So what are going to be some of the specific consequences that we expect to see? What are going to be some of the specific things that climate change is expected to do to our world if we continue to have this kind of warming? Well, the most obvious is that we're going to have many more very hot days and fewer very cold days. So this little dog has got some heat exhaustion, has kind of collapsed on the floor. He is unfortunately going to have to deal with that much more often under a scenario of a high level of climate change. So that means that we're going to see more heat stroke and less frostbite in our world. We're also going to see increased drought in those areas that see a decrease in precipitation. So someplace like the southwestern United States is already in a long-term drought. There's already a great deal of water stress in that area. The Colorado River is the main water source for the Southwest. Its water is already over-allocated. There are more people with claims on that water than there is water to go around right now as a result of big population growth in Arizona and Southern California and Nevada. The Colorado River, by treaty, is supposed to flow into Mexico at the end. Mexico is entitled to a certain amount of water from the Colorado. But the Colorado has not actually flowed into Mexico for many years because all that water is being used up while it's still in the United States. And so if conditions in the Southwest get even drier, we will have an even worse drought crisis there. And likewise for other parts of the world where we expect increased drought as a result of climate change. On the other hand, areas that we expect to see increased rainfall under climate change, we'll see more flooding, we'll see more big storms. This is one particularly controversial issue because there's a widespread claim that climate change is causing increased strength of hurricanes around the world. But if we look at the actual hurricane data that we have, because there's only a few hurricanes a year, our data set on hurricane strength has a lot of variability in it. It's hard to see a clear trend thus far. So we expect, based on our understanding of the global climate system, that as we go into the future, if there's continued climate change and continued warming of the Earth, that we would see increases in hurricane strength. But we can't say for sure that we're seeing that already. This became a big issue with things like Hurricane Katrina back in 2005. Many people wanted to point to Hurricane Katrina as having been caused by climate change. That climate change caused this devastating hurricane that wiped out the city of New Orleans. But we can't actually say that. We can't say that of any one weather event. The best that we can say, what we should say if we want to be careful about how we're explaining climate change, is that giant devastating hurricanes like Katrina are the kind of thing that we expect to see more frequently if we have continued climate change. So we can never blame any one weather event on climate change. That weather event by itself might still have happened without climate change. But the overall pattern, the overall frequency of certain types of weather events, we can pin on climate change. So if we accumulate more data through future hurricane seasons and start to see a clear upward trend, then that upward trend we can attribute to climate change, even if we can't blame climate change for any one hurricane. We also expect to see increased wildfires. As a result of increased temperatures and lower precipitation levels, we're going to increase the conditions for big, catastrophic sorts of wildfires in places like Southern California and Australia. We actually do have enough wildfire data. There are enough wildfires going on in the world each year that we can actually see a clear trend. So we have actually been able to scientifically document a correlation between increases in the size and severity of wildfires in the United States and in some other parts of the world as correlated to increases in our global temperatures. We also expect climate change to have impacts on agriculture. If we have changes in the amounts of precipitation and changes in the temperature, we're going to see certain areas become more suitable for agriculture and other areas less. Specifically, Canada and Russia we expect to gain agriculturally from climate change. The increased warming will make more areas of the Siberian and Canadian plains suitable for growing major crops. On the other hand, other parts of the world, especially in the tropics, we expect to see decreases in the suitability of those areas for agriculture, and so decreases in agricultural yield. And so it's important to consider in this context both the overall balance of increase and decrease in agricultural output and who is gaining and who is losing. And so what we find is that overall, when we weigh the areas that would be able to grow more food as a result of climate change and the areas that would be able to grow less, we see a net decrease in our global food supply if we have continued high levels of climate change. So the extra food that can be grown in Siberia and Canada is not going to make up for the decrease in more tropical areas. Furthermore, the areas that stand to gain from climate change are generally those areas that are already pretty well off. Canada, for example, is a very rich country already. On the other hand, a country like Zimbabwe, where we expect big decreases in agricultural output from climate change, is a very poor country, a country that can't really afford to lose very much agricultural output. We also expect climate change to lead to death of coral reefs. And this is for two reasons. One is changes in our ocean temperature. As our whole planet's warming up, our oceans are also warming up. And in fact, the oceans are absorbing a huge amount of the increases in the sun's energy that's being trapped on the Earth. If we didn't have the oceans as these big reservoirs taking on some of this warmth, our increases in land temperature would be far higher than we've actually experienced. But those increasing temperatures in the ocean are bad for coral. Coral is a very fragile ecosystem, and so if you warm the ocean by just a little bit, you can kill off that coral. We also have ocean acidification happening. So when that carbon dioxide is put into the atmosphere, not only does it act as a greenhouse gas, it also gets absorbed by the ocean. So this again offsets some of our climate change. If it weren't for the oceans absorbing this CO2 out of the atmosphere, we would see even more climate change than we're already seeing. However, absorbing this extra CO2 into the oceans increases the acidity of the oceans. It lowers the ocean's pH value. And so as the ocean water becomes more acidic, it becomes less hospitable to many ocean species. So between increases in ocean temperature and increases in ocean water acidity, we're seeing die-offs on coral reefs all around the world. And coral reefs are an essential ocean ecosystem. Finally, we have sea level rise. Increasing temperatures on our Earth are going to bring increasing sea levels. This means that many coastal areas are at greater risk of being flooded. There are huge populations on the Earth living right along the coast. We have so many coastal cities. We have places like Bangladesh where there are huge numbers of people farming in areas that are just a meter or two above sea level. And so sea level rise stands to wipe out those areas. So it could be incredibly devastating. There are some entire countries that stand to completely disappear as a result of climate change. If those countries are located on low-lying coral islands in the ocean, so we're talking here about countries like the Maldives in the Indian Ocean and Kiribati in the Pacific Ocean. If they get just a meter or two of sea level rise, which is well within our projections for just the next century, those entire countries could disappear under the water. And that could create not only a great human tragedy in and of itself, but then also a major refugee problem for surrounding areas as the people flee these sinking areas and try to find another place to live. There are two basic reasons why climate change, why a warming of our Earth's atmosphere would cause sea level rise. The first thing that happens is glacial melt. As our Earth warms, our glaciers have begun to melt. Our continental ice sheets in particular are contributing huge amounts of water to the ocean as they melt in Greenland and in Antarctica, and that melted water is added to our oceans. That glacial melt accounts for about half of the sea level rise that we've seen thus far, and about half of the sea level rise that we expect to see over the next century. The other half of that sea level rise is caused by what we call thermal expansion. So when water warms up, it swells just a little bit. It's not enough that you're going to notice it. If you put a pot of water on the stove and turn the heat on, you're not going to see that water level go up noticeably. But when you have as much water as you have in the entire oceans of the world, then a little bit of thermal expansion as that ocean water warms is going to push up that sea level by a noticeable amount. So between glacial melt and thermal expansion, climate change is going to cause a significant rise in our sea levels and therefore a devastation to coastal areas that are going to be flooded by this.